There is one number you have known for most of your life, a number so familiar it feels less like a fact and more like furniture. The universe is 13.8 billion years old. It is printed in every textbook, recited in every classroom, treated as settled as the speed of light. But a few years ago, we built a golden telescope, flew it out into the cold 1 million miles from Earth, and pointed it at the very beginning of time. And it sent back something that should not exist. Galaxies, sitting at the edge of everything we can see, that appear too heavy, too bright, and too finished for the sliver of time they were given. Some look as developed as our own Milky Way, which had more than 13 billion years to grow, except these had only a few hundred million. They look impossibly older than the universe that holds them. Get comfortable. Hit subscribe if you're new here. Because by the end of this, that number you have always trusted will feel less like a wall and more like a question. Now, let's slowly ease into this. Part 1. The mirror we built to see the beginning. For a long time, the beginning of everything was a place we could only reason about, never look at. We could measure the faint warmth left over from the birth of the cosmos, the gentle hiss of radiation that fills the sky in every direction, and from that warmth we could work backward to a moment when the whole universe was hot and dense and shapeless. But the first galaxies, the first true islands of a light that switched on after the long darkness, sat just beyond our reach. They were too faint, too far, and their light too stretched by the expansion of space for any instrument we owned to gather it. So we built one for the purpose. We spent decades and billions and the patience of thousands of people to build a single machine whose only real job was to look at the dawn. On the 25th of December, 2021, that machine left the Earth. The James Webb Space Telescope rode a rocket up through the atmosphere, and then it did something that no telescope its size had ever done in space. It unfolded. A mirror 6.5 meters across, made of 18 segments coated in a microscopically thin layer of gold, opened like a flower in the cold. A sunshield the size of a tennis court stretched out beneath it, layer by layer, to hold back the heat and the glare of the sun. The telescope drifted out to a quiet gravitational balance point about 1.5 million kilometers from home, 4 times farther than the moon, and there it began to cool. It cooled until its instruments hovered just a few tens of degrees above absolute zero, the coldest temperature there is, because to see the faint infrared light of the first galaxies, a telescope must be colder than the thing it is trying to detect. Anything warmer would drown the signal in its own glow. The choice of infrared was the whole point. When light travels across an expanding universe for billions of years, the expansion stretches it. A wave that left a young galaxy as ultraviolet or visible light arrives at our detectors pulled out into longer, redder wavelengths, shifted out of the range our eyes can see and out of the range that older telescopes could easily gather. The farther away the source, the longer the journey, and the more its light is stretched. By the time the glow of the very first galaxies reaches us, it has been pulled far into the infrared. Hubble, for all its triumphs, could barely touch that band. Webb was built to live there. It was, in a real sense, a telescope designed to read the most faded handwriting in the universe, the messages that had been travelling the longest and had been worn the thinnest by the road. Think about what that means for a moment. When you look at the most distant object Webb can see, you are not seeing it as it is now. You're seeing light that left it more than 13 billion years ago, before the Earth existed, before the Sun existed, before most of the atoms in your body had been forged inside any star. That light has been crossing empty space this entire time, outrunning nothing, simply travelling, while galaxies formed and died, and the Sun was born and life crawled out of the oceans and learned to build telescopes. The photon that ends its journey inside Webb's detector is a genuine messenger from the youth of the cosmos. It is the closest thing to time travel that physics permits. You cannot go there, but the light can come here, and it carries the past inside it, perfectly preserved. The people who built Webb knew, in broad terms, what they expected to find at the edge of time. The standard model of cosmology, the framework that has survived test after test for decades, makes a clear prediction about the early universe. It says that structure builds slowly, from the bottom up. In the beginning, there were only faint ripples in the density of matter, regions very slightly denser than their surroundings. Gravity went to work on those ripples, pulling matter inward, and over time the small clumps grew and merged into larger ones. The first galaxies in this picture should be small. They should be faint. They should be ragged and irregular and few, the half-assembled seeds of the grand spiral and elliptical galaxies that would take billions of years to grow. Astronomers aimed Webb at the dawn, expecting to find a nursery full of newborns, dim and tiny and just beginning. That expectation was reasonable. It was built on the best physics we have, confirmed by the leftover radiation of the Big Bang, confirmed by the way galaxies cluster across the sky, confirmed by the abundance of the lightest chemical elements, confirmed by a dozen independent lines of evidence that all agree the universe is about 13.8 billion years old, and that it grew its structure gradually. Nobody aimed the most expensive telescope ever built at the early universe expecting to be frightened by it. They expected confirmation. They expected to fill in details, to see the faint seeds a little more clearly, to refine the numbers. The first galaxies were supposed to be a quiet chapter, a gentle filling in of a story we already mostly knew. The first full-colour images arrived on the 12th of July, 2022. They were beautiful, and the public marvelled at the sharpness, the clarity, the sheer reach of the thing. But within those same fields, scattered among the expected faint smudges, sat a few points of light that did not belong. They were compact, they were red, and when the astronomers ran them through their analysis, the numbers that came back were wrong in a way that made people stop and look again. These little red points were not the faint seeds anyone had ordered. The data insisted they were enormously far away, which was expected, and enormously large, which was not. They looked like they had no business existing so early, and the more carefully people looked, the worse the problem became. It is worth pausing on what we even mean by the dawn, because the word gets used loosely and the reality is precise. After the Big Bang, once the universe had cooled enough to become transparent, there came a long stretch with no stars at all, only an expanding sea of hydrogen and helium gas, dark and smooth and slowly cooling. Astronomers call that stretch the cosmic dark ages, and it lasted for something like 100 million years or more. The dawn is the end of that darkness, the moment the first stars and the first galaxies ignited and began to pour light back into a universe that had known none. Their radiation gradually tore apart the neutral hydrogen that filled space, splitting it back into charged particles, in a transformation astronomers call rionization. To watch the dawn is to watch that first light switching on and clearing the fog a second time, and it is the single hardest thing in all of observational astronomy, because the objects are the faintest and the most stretched of anything we can hope to detect. That is the reason this particular telescope had to be built, and built exactly as it was. No instrument that came before could reach that light cleanly. The first galaxies are not just dim, their light has been pulled so far into the infrared that earlier telescopes were nearly blind to it. To see the dawn, you need a mirror large enough to gather a pitiful trickle of ancient photons, an observatory cold enough that its own warmth does not swamp the signal, and detectors tuned to exactly the wavelengths into which the universe has stretched that first light. Webb was the first machine in history to combine all three. It was not built to take pretty pictures, though it takes them. It was built to be a time machine pointed at the first morning, and the people who built it understood that they were gambling decades of work and a generation of careful planning on a single, fragile, unrepeatable unfolding in the cold. We will spend this long night together pulling that problem apart slowly and patiently, the way you would untangle a knot you're in no hurry to finish. We will follow the discoveries as they actually arrived, in order, because the order is part of the story. We will ask how we even know how old the universe is, so that we understand exactly what these galaxies seem to be violating. We will find that this is not the first time the cosmos has handed us something that looks older than itself, and that the last time it happened, the fear turned out to be a teacher. By the end, the title of this video will mean something different than it does right now. But for that to happen, we have to begin where the astronomers began, with a handful of red dots that refuse to make sense. So let us look at them closely, and ask why a few smudges of ancient light were enough to unsettle an entire field. Part 2. The first dots that refused to make sense. The objects that started the trouble did not look like much. In the long exposure images they were tiny, compact and red, easy to mistake for nothing in particular. To understand why they cause such alarm, you have to understand what astronomers do with a smudge of light to turn it into a fact. They cannot simply look at a distant galaxy and read off how big it is or how far away. The galaxy is a single point, or barely more than a point in the field. What they have instead is its colour, measured across several bands of infrared light, from the shorter wavelengths to the longer ones. That spread of brightness across wavelength is called a spectral energy distribution, and it is the fingerprint from which everything else is inferred. The colour tells you first how far away the galaxy is. As we said, the expansion of the universe stretches light, and the farther the galaxy, the more its light is shifted toward the red. There is a particular feature in the light of galaxies, a sharp drop at a specific wavelength caused by hydrogen absorbing the most energetic photons, and by watching where that drop lands in the spectrum, astronomers can estimate the redshift, the amount the light has been stretched, and therefore the distance and the age. When the drop is shoved far into the infrared, the galaxy is very distant and very young. This method is powerful, and it has found most of the record-breaking galaxies we know. But it is an estimate built from a handful of broad colour measurements, not a precise reading, and that distinction will matter enormously before the night is over. The colour tells you something else too. The overall brightness, combined with the distance, gives you the total amount of light the galaxy is pouring out. And the particular shape of the colour, how much light comes out in the bluer bands versus the redder ones, lets astronomers estimate how many stars the galaxy contains and how heavy those stars are in total. A galaxy that is red and bright, seen when the universe was very young, is telling you a particular and troubling story. The redness suggests either a great deal of dust or a population of older stars, or both. The brightness suggests a great deal of mass. Put those together at an early enough time and you get an object that seems to contain far more stars than it should have had time to make. This is exactly what the first alarming objects looked like. They were red, which hinted at maturity. They were bright, which hinted at mass. And they were very distant, which meant they were being seen when the universe was only a few 100 million years old. The analysis routines, fed this combination, returned stellar masses that were staggering. Not the modest masses of half-formed seeds, but the masses of grown galaxies, galaxies as heavy as the great spirals that surround us today, somehow already assembled in the first sliver of cosmic history. The first time a number like that comes back from your software, you do not believe it. You assume you have made a mistake. That assumption is healthy, and the astronomers made it. They checked their calibrations. They checked whether the galaxies might be much closer than they appeared, with their red colour caused by dust rather than by distance. They checked whether contamination from nearby sources was inflating the brightness. They checked whether the instrument itself was introducing some artifact. Science at this level is mostly the discipline of trying to prove yourself wrong before someone else does it for you, and the people working with this data were among the best in the world at exactly that discipline. They wanted the simple explanation. They went looking for the mistake that would make the problem disappear. Let us sit inside that moment for a while, because it is the human core of this whole story. Picture the room, or more honestly the screen, late at night. A researcher has a compact red source pulled up in the analysis software. The fitting routine has just returned a stellar mass that should not be possible for an object seen this early, a number that would mean this little smudge had built itself into something as heavy as the entire Milky Way, while the universe was still in its infancy. The first feeling is not wonder. The first feeling is suspicion. There must be a bug. So the researcher changes a setting and runs it again. The same number comes back. They swap in a different model for the dust, a different assumption about the stars, a different calibration of the filters. The number moves a little and then it settles stubbornly back into the impossible range. They pull up a second object and a third, and the pattern holds. These are not random flukes. The data are saying the same thing over and over, calmly, the way data do, with no awareness that they are breaking anything. It is worth sitting in the quiet of that scene a little longer, because it is the kind of moment that almost never makes it into the textbooks, and yet it is where the real work of science actually lives. There is no drama in the room, no alarm, no sudden discovery in the cinematic sense. There is only a person and a screen and a number, late at night, and the slow dawning that the number is not going to cooperate. The galaxy on the screen does not look frightening. It is a faint smudge, a handful of pixels, easy to overlook. Everything alarming about it lives entirely in the arithmetic, in the gap between what the smudge implies and what the universe is supposed to allow. And the person staring at it is not a distant authority. They are someone doing their job carefully, feeling the particular loneliness of being the first to see something that does not fit, and not yet knowing whether it is a mistake, a discovery, or the beginning of a long argument that will outlast the night. There is a particular quality to that kind of fear. It is not the sharp fear of danger. It is the slow, cold fear of a number that will not go away. Anyone who has ever rechecked a result they desperately hoped was an error knows the feeling, the way you keep approaching it from new angles, certain that this time the mistake will reveal itself, and the way the certainty erodes a little with each pass that comes back the same. For the astronomers looking at these early galaxies, that feeling was not about a homework problem or a spreadsheet. It was about the structure of the universe. The number that would not go away was telling them that the cosmos had built something too big, too soon, in a way their best theory said it could not. It is worth understanding why this particular kind of measurement is so slippery, because the slipperiness is at the centre of everything that followed. When you fit a model to a galaxy's colours, you are solving a puzzle with more unknowns than you have clues. The same observed colour can be produced by very different galaxies. A red glow can mean an object so distant that its light has been stretched far into the infrared. It can also mean a closer galaxy reddened by thick dust, the way the setting sun turns red through a smoky sky. It can mean a population of older, cooler stars. It can mean some mixture of all three. The fitting software does its best to find the most likely combination, but it is choosing among possibilities that genuinely overlap, and a small change in the assumptions can swing the answer toward a very distant, very massive galaxy, or toward a nearer, more modest one. This is not a flaw the astronomers were hiding. It is a known and openly discussed limitation of working from colours alone, and it is precisely why the field treats photometric results as candidates rather than conclusions. The way you settle the question is to spread the light into a true spectrum, fanning it out into its component wavelengths the way a prism fans sunlight into a rainbow. In a spectrum, the fingerprints become unmistakable. Specific features, emission, and absorption lines from particular elements appear at particular wavelengths, and from their positions you can read the distance with precision rather than estimate it. But spectroscopy is expensive. It demands far more of the telescope's time, hours of staring at a single faint object instead of a quick snapshot of a whole field. So the early alarm came from the fast method, the colours, and everyone understood that the slow method, the spectra, would have the final word. The first red dots were a question, not an answer, and the people who found them said so out loud. What they were holding, though they did not yet know how it would resolve, was the leading edge of one of the most interesting scientific puzzles of the decade, and crucially they did not hide it. The instinct of someone who has truly found a mistake is to fix it quietly. The instinct of someone who has found something real and strange is to tell the world and ask for help. The team that had been staring at these impossible red dots chose the second path. They prepared to publish, in the most visible journal in science, a result that they themselves could barely believe, with a claim attached to it that would put the word impossible into headlines around the world. To understand why that took a certain kind of courage, and why the claim landed as hard as it did, we have to look at exactly what they found, and exactly how heavy these galaxies at the edge of time appeared to be. Part 3. The Galaxies that Broke the Universe. In February 2023, a team led by the astronomer Ivo Labbé published the result in the journal Nature. The paper had a careful technical title about a population of red candidate massive galaxies seen roughly 600 million years after the Big Bang. The careful title did not survive contact with the public. What survived was the phrase that captured what the result felt like, the phrase that ran across the internet and through newsrooms and into ordinary conversation. These were the universe breakers, and Labbé's own description of the discovery became the line that everyone repeated, because it was honest in a way scientists are rarely willing to be in public. It was, he said, as if they had discovered the impossible. The paper examined 6 galaxies, seen as they were between about 500 and 700 million years after the beginning. That window sounds enormous when you say it in years, but against the full 13.8 billion year history of the cosmos, it is the first few minutes of a very long day. And in that first few minutes, these 6 objects appeared to have already assembled an astonishing quantity of stars. The inferred masses ran upward, object by object, until the most extreme of them approached 100 billion times the mass of the Sun. To put that number where you can feel it, That is comparable to the entire stellar mass of the Milky Way, the galaxy we live in, the galaxy that has had more than 13 billion years to gather and forge its stars. One of these objects seemed to have done nearly the same work in less than a 20th of the time. To see why that is not merely surprising but genuinely threatening to the theory, you have to understand the speed limit involved. In the standard model, galaxies are made of stars and stars are made of gas, and the gas is made of ordinary matter that has fallen together under gravity into a galaxy-sized clump. There is only so much ordinary matter that can have collapsed into any given region by a given time, because gravity needs time to do its pulling, and the universe was expanding the whole while, working against the gathering. That sets a ceiling. Given the amount of matter available in a region that early, there is a maximum number of stars that could possibly have formed, even if every single atom of available gas were turned into a star with perfect, total, lossless efficiency. The most extreme of these galaxies pressed against that ceiling, and in some readings appeared to exceed it. They seemed to contain more stars than the available gas could have made, even running the furnace at an impossible 100%. Let the comparison to our own galaxy sink in for a moment, because it is the detail that makes the result land in the body rather than the head. The Milky Way, the galaxy you live in, the one whose faint band you can see arching across a dark sky on a clear night, contains on the order of 100 billion stars. It has been gathering and forging those stars for more than 13 billion years, building itself slowly through a long succession of mergers and quiet star formation, one generation lighting up as the last one fades. It is, by any measure, a grand and mature spiral, the product of nearly the entire history of the universe. And here was a smudge of red light, seen when the cosmos was a few 100 million years old, that the data claimed had already assembled a comparable horde of stars. It was as though you returned to a construction site you had watched for years, expecting to find the foundation barely poured, and discovered instead a finished cathedral, complete to the spire, built in an afternoon. The arithmetic of that is what made it feel less like a surprise and more like a violation. To match the Milky Way's stellar mass in a 20th of the time, a galaxy would have to have built stars at an average rate dozens of times faster than anything we see in the mature universe, sustained over its whole brief life, and it would have had to do so from a supply of raw gas that the early universe may not even have been able to gather that quickly into one place. Each link in that chain strained against the physics. The gas had to arrive too fast, gather too densely, and convert to stars too efficiently, all at once, all in the first sliver of cosmic time. It was not one improbable thing. It was a stack of improbable things, each one leaning on the next, and the whole stack was what made experienced astronomers sit back from their screens. That is what made the result feel like a break rather than a surprise. A galaxy that is merely bigger than expected is interesting. A galaxy that seems to contain more stars than the laws of structure formation allow is a different thing entirely. It is the cosmic equivalent of finding a building that contains more bricks than were ever delivered to the site. Either the bricks came from somewhere you do not understand, or your records of what was delivered are wrong, or you're miscounting the bricks. None of those options is comfortable, and in early 2023 nobody knew which one was true. What they knew was that 6 smudges of ancient red light had walked up to the standard model of cosmology and asked it a question it could not immediately answer. I want to slow down here and stay with the people, because it is easy to talk about a result like this as though it simply appeared, fully formed, in a journal. It did not. Behind it were months of exactly the suspicion we described, the rerunning and rechecking, the search for the mistake that would make it all go away. And at the end of that search, the team faced a choice that carries a particular kind of weight. They could soften the claim, hedge it into something safe and forgettable, or they could state plainly what their data showed and let the field react. They chose to state it plainly. They put the word impossible next to their result and published it in the most visible venue in science, knowing that if they were wrong, they would be wrong loudly, in front of everyone. There is courage in that, and it is worth naming because it runs against the way we usually imagine scientists. We tend to picture science as cold and certain, a march of confident facts. But the most important moments in science are often the opposite. They are moments where a person looks at a result that contradicts everything they were trained to expect, feels the full discomfort of it, and decides to tell the truth about what they see rather than what they wish they saw. Anyone who has ever had to say the unpopular thing in a meeting, to raise their hand and admit that the numbers do not add up when everyone around them wants to move on, knows a small version of this feeling. The Labby team felt the large version. They told the world that their own telescope had broken their own field's expectations, and they invited everyone to come and check. The reaction across the field was not quiet acceptance, and it should not have been. When a result threatens a framework that has passed every previous test, the right response from everyone else is vigorous skepticism, and that is exactly what the universe breakers received. Other astronomers pointed immediately to the fragility of the masses. They noted that the most extreme values depended on assumptions about the stars and the dust that could be pushed in more conservative directions. They argued that if you adjusted the model in reasonable ways, several of the galaxies became less alarming, still surprising but not necessarily impossible. They pressed, correctly, for spectra, for the slow and decisive measurement that would either confirm the masses or deflate them. This back and forth is sometimes mistaken from the outside for the experts contradicting themselves or for the result falling apart. It is neither. It is the immune system of science doing its work, the way a strong claim is supposed to be tested from every side before it is allowed to stand. What survived that testing was important, and it is worth being careful about. The most extreme single estimates softened under scrutiny, as extreme estimates usually do. But the broader pattern did not simply vanish. Even after the skeptics had their say, the early universe still looked more crowded with bright, substantial galaxies than the pre-launch models had predicted. The headline number, the one galaxy supposedly as heavy as the entire Milky Way, was the most vulnerable part of the claim, and the part that bent the most. The underlying tension, that the cosmos seemed to have built too much too brightly too soon, was more stubborn. It bent, but it did not break, and it kept reappearing in object after object as the surveys reached further. That is what made this more than a single dramatic paper that might quietly be forgotten. It was the loud opening of a problem that would not go away. That invitation mattered, because the claim, as published, rested on a particular kind of evidence, and that kind of evidence has a known weakness. The masses and distances were photometric. They were inferred from the spread of brightness across a handful of broad infrared filters, not measured by spreading the light into a full detailed spectrum. Photometry is fast and it lets you survey many objects at once, which is how you find rare things in the first place. But it is a sketch, not a portrait. A red, bright, compact source can be a distant, massive galaxy. It can also be a dustier, closer galaxy wearing a disguise. It can be something stranger hiding at its center. The honest version of the Universe Breakers result always carried that caveat inside it, written by the authors themselves. These were candidates. The real test would come when the light could be spread into a true spectrum and read line by line. So the discovery did two things at once. It announced a genuine crisis, a real tension between observation and theory that could not be waved away. And it announced, in the same breath, the precise reason the crisis might soften, the fragility in the measurement that follow-up work would have to probe. Both halves of that are essential, and we will follow both. But first, the records kept falling. While the field argued about whether the universe breakers were truly as massive as they looked, Webb kept pushing farther, and it found something even more disorienting than a galaxy that was too heavy. It found a galaxy that was too far, sitting almost at the literal edge of what can be seen, in a place so early that its very existence raised the same question in an even sharper form. To stand at that edge, we have to follow a single beam of light all the way back to the beginning. Part 4. The Edge of Time Itself. The most distant galaxy we have confirmed carries an unromantic name. It is called Jade's GS Z14-0, a label assembled from the survey that found it and its place in a catalogue. But the name hides something staggering. The light we collect from this galaxy left it when the universe was only about 290 million years old. Set against 13.8 billion years, that is the first 2% of cosmic history. If you compressed the entire age of the universe into a single year, with the Big Bang on the 1st of January and this present moment at the final stroke of midnight on the 31st of December, then the light from this galaxy left it in the first few days of January, while the cosmos was still by every measure a newborn. The galaxy was found by spreading its light not just across a few broad filters, but into a true spectrum using Webb's near-infrared spectrograph. In 2024, the instrument stared at this single faint object for nearly 10 hours, gathering its light photon by photon, until the spread of that light could be read in detail. The reading gave a redshift of about 14.3, the highest ever confirmed for a galaxy. Later, astronomers detected a specific fingerprint of oxygen in its light, an emission line at a wavelength of 88 microns, which pinned the distance down even more firmly. This was not a photometric guess. This was a measured, confirmed object, sitting almost as far back in time as our instruments can presently reach, and it too refused to behave. Theory predicted that a galaxy seen this early should be a faint, tiny, struggling thing, barely lit. Jade's GZ-0 is over 1,600 light-years across, which is small for a galaxy, but large for something supposedly just beginning, and it is surprisingly luminous, blazing with the light of young, hot stars. Among the hundreds of high redshift galaxies surveyed, the astronomers could find no good analogue for it. It does not look like the objects the models predicted for its epoch. It looks like a galaxy that has gotten further along than it should have, brighter and more developed than the early universe was supposed to permit. Then there is the oxygen, which is its own quiet shock. Oxygen does not exist at the beginning. The Big Bang produced hydrogen, helium, and a trace of lithium, and nothing heavier. Every oxygen atom in existence was forged in the core of a star and then scattered into space when that star died. For a galaxy to already be salted with oxygen when the universe was only 290 million years old, an entire prior generation of stars must have already lived, fused their hydrogen up into heavier elements, exhausted themselves, and exploded, seeding the surrounding gas with the ash of their making. And all of that must have happened fast in the first sliver of time, before the light we now see ever set out. The galaxy we are looking at is already a second draft. The first draft has already burned and gone. Let me take you there, because numbers on their own can keep this at arm's length, and it deserves to be felt. Imagine you could ride a single photon backward along its path, the way you might trace a river upstream to its source. You start here, in the present, at a detector floating cold and silent 1.5 million kilometers from Earth. You catch the photon at the instant it arrives, and you turn around and follow it back the way it came. You travel back across the emptiness for billions of years. The galaxies thin out and grow younger and bluer as you go. The sun winks out of existence behind you, never having formed. The familiar constellations dissolve. Still you travel, past the era when the great spiral galaxies were assembling, past the bright violence of the young cosmos, until the universe around you is a different place entirely, smaller, hotter, packed more tightly, lit by stars that are only a few generations old, and then you arrive. Ahead of you is the source, the galaxy, as it was 290 million years after everything began. It is not the grand pinwheel you might picture. It is a fierce, compact knot of blue-white light, a furnace of young stars burning hard and fast, packed into a space barely more than 1,000 light-years across. It is small, and it is intense, and it is already, impossibly, carrying the oxygen of a generation that has come before it. There is no Earth to look back toward, because the Earth will not exist for more than 9 billion years. There is no one here to see this but you. This is the dawn, or very near it, and the dawn is already further along than the textbook said it could be. You are standing in the first 2% of time, looking at something that seems to have skipped ahead. That is the sensation the astronomers were grappling with, translated out of the equations and into a place you can stand. The galaxy at the edge of time is not faint and struggling. It is bright and developed and chemically seasoned, and it sits so early that there scarcely seems to have been time for any of it. The record holder was not an outlier that could be dismissed. It was the sharpest possible version of the same problem the universe breakers had posed. The early cosmos kept producing objects that looked like they had more history behind them than history could supply. Consider what it took to confirm a single object like this, because the effort is part of why the result carries such weight. The galaxy was first picked out as a candidate in the imaging, one faint smudge among many, flagged by its colours as a possible record breaker. To turn that candidate into a confirmed distance, the astronomers had to commit the telescope to staring at it, gathering its trickle of light for the better part of half a day, building up enough signal that the spectrum could be read. Then they had to find, in that spectrum, the unmistakable features that fixed the redshift beyond argument. The break in the light where the intervening hydrogen of the young universe absorbs everything beyond a certain wavelength. The faint emission lines from the galaxy's own gas. When those features line up at the wavelengths that a redshift of about 14 predicts, the distance is no longer a guess. It is measured. This was not a number pulled from a quick fit to a few colours. It was a hard-won, spectroscopically confirmed fact, which is exactly why it could not be waved away as a photometric mirage. The survey that found it is a sustained, deliberate program, one of the flagship efforts of the whole mission, designed to map the early universe galaxy by galaxy and to confirm the most important objects with spectra. That matters because it means JD's GS Z14-0 is not a lucky accident stumbled upon at the edge of a single image. It is the brightest and most developed member of a growing catalogue of confirmed early galaxies, surrounded by hundreds of others at slightly lesser distances, and against that whole population, it still stands out as too luminous, too substantial for its moment in cosmic time. A single strange object can be dismissed as a fluke. A record holder that refuses to fit sitting atop a whole population that also leans brighter than expected is a pattern. And patterns are what force a field to take a problem seriously rather than filing it away as an oddity. But notice something about how we got here. We have been talking the whole time as though we know, with confidence, exactly how old the universe is and exactly how much time these galaxies did or did not have. We have been treating 13.8 billion years as a fixed and trusted ruler against which these objects are being measured and found impossible. Before we can decide whether the galaxies are truly breaking anything, we have to turn that assumption around and examine it. How do we actually know how old the universe is? Where does that number come from, and how much should we trust it? Because the whole sense of crisis depends on the ruler being reliable. If the galaxies look older than the universe, we had better be very sure we know how old the universe is. So let us put the galaxies down for a while and pick up the clock. Part 5. The word for the fear. We should be precise about what is actually frightening here, because the fear is easy to mislabel. The natural assumption, hearing that astronomers found galaxies that disturbed them at the edge of the universe, is that the problem is distance. It is not. Distance is the one thing about these objects that is entirely expected. The whole purpose of building Webb was to see farther than ever before, to push our vision back toward the beginning. A galaxy being far away, a galaxy being seen as it was when the universe was young, is not a scandal. It is the point. If the only surprising thing about these objects were how distant they are, there would be no story, only a triumph. The frightening thing is not distance, it is maturity. And the difference between those two words is the difference between a quiet result and a crisis. A galaxy that is merely far away is, by definition, a galaxy we are seeing in its youth, because its light is old and shows us the past. A young galaxy should look young. It should be small, because it has not had time to grow. It should be blue, because it is full of hot young stars and not yet reddened by age or thick with the dust of many stellar generations. It should be irregular, a ragged clump still pulling itself together, not an organized structure. It should be light, holding only the modest mass it has had time to gather. Youth has a particular appearance, and we know what it is. These galaxies look the opposite. They looked old. They were heavy where they should have been light, as though they had been gathering mass for ages. Some were red in a way that suggested either thick dust or older stars, both of which take time to develop. Some, found in later observations, showed orderly rotation, spinning in flattened disks the way settled, structured galaxies do, rather than tumbling in the chaos of the early assembly. And as we saw, some already carried heavier elements like oxygen, the chemical signature of generations of stars that had already lived and died. Every one of these traits is a marker of time elapsed. Mass takes time to gather, dust takes time to accumulate, rotation takes time to organize, heavy elements take time to forge. To find all of that at the edge of the observable universe is to find the appearance of long history in a place where there had been almost no history at all. That is the precise sense in which these galaxies look older than the universe that contains them. It is not that anyone seriously believes an object can be literally older than the cosmos it sits inside. That would be a contradiction in terms, like a child older than its parent. The phrase is a description of an appearance, and the appearance is the problem. These objects wear the features of age in an epoch that had no time to grow them. They look like the products of billions of years of evolution, glimpsed in a universe that was only a few 100 million years old. The clock on the wall says it is early morning, and yet the figures in the room are dressed for the end of a very long day. When you put it that way, you can feel why it unsettled professionals so badly. The age of the universe is not some obscure technical quantity that only specialists care about. It is one of the few genuinely cosmic facts that ordinary people carry around in their heads, 13.8 billion years. It is printed in textbooks, recited in classrooms, quoted in documentaries, treated as one of the bedrock numbers of reality, as settled as the speed of light or the freezing point of water. It is the kind of fact that feels less like a measurement and more like a commandment, something handed down and fixed. And these galaxies were the first thing in a generation to make professional cosmologists wonder out loud, in print, in the most prestigious journals, whether that number or the story we hang upon it might be incomplete. There is a particular vertigo in that. Most of the time, when our understanding of the world is challenged, it is at the edges, in some specialized corner that does not touch the things we feel sure of. This was different. This reached toward the center. It reached toward the timeline itself, the framework on which every other cosmic fact is hung. If the age of the universe is uncertain, or if the story of how that age was filled with structure is wrong, then a great many things we thought we understood become unsteady at once. When the most basic fact you were taught about time itself starts to wobble, everything built on top of it wobbles too. That is the feeling the galaxies produced. Not fear of a thing out there in the dark, but the quieter unease of solid ground turning soft beneath a familiar number. Let me dwell on one of those markers of maturity in particular, because it is the most quietly devastating of them, and it is easy to pass over. Some of these early galaxies show rotation. They spin in flattened, orderly disks, the way a settled spiral galaxy like our own turns slowly about its center. That may not sound dramatic, but think about what rotation requires. A newborn galaxy, fresh from the chaos of assembly, is a mess. It is matter falling together from many directions at once, clumps colliding, gas churning, nothing organized. To settle that chaos into a smooth, rotating disk takes time and many orbits, the way a swirl of cream in coffee only gradually organizes itself into a single turning pattern. A galaxy that has already settled into an orderly disk has, in a real sense, lived long enough to grow calm. To find that calm at the edge of the observable universe, in an object seen when the cosmos was only a few 100 million years old, is to find a kind of composure that should not yet have had time to develop. The same is true of the heavy elements, and it is worth feeling the full strangeness of it. Every atom heavier than hydrogen, helium, and a trace of lithium was forged inside a star. Carbon, oxygen, nitrogen, iron, the very elements your body is built from, did not exist at the beginning. They were cooked, one generation of stars at a time, in stellar cores, and scattered into space by stellar deaths. For an early galaxy to already contain these elements means it has already run at least one full cycle of stellar life and death, born stars watched them age and absorbed their ashes, all before the light we now see ever left it. Maturity, in a galaxy, is not a vague impression. It is mass that took time to gather, rotation that took time to settle, and chemistry that took generations of stars to brew. Finding all three at once so early is the precise shape of the problem, and it is why the word that kept surfacing was not surprising but impossible. And yet I want to plant a seed here that we will return to at the very end, because the fear, real as it is, has a shape that should be recognized rather than simply suffered. The phrase older than the universe is not new. It did not arrive with Webb. It has a history in astronomy, a recurring history, and every previous time the cosmos has handed us something that looked older than itself, the phrase has turned out to mean something specific and survivable. It has never once meant a true paradox, a genuine logical contradiction in the fabric of reality. It has always meant that two of our measurements disagreed with each other, and that the disagreement was about to teach us something we did not know. Hold that thought. We are not ready to use it yet. First we have to earn it, by understanding exactly how the clock works that these galaxies appear to violate. Because here is the thing about a measurement crisis. It only has force if you trust the ruler. If you tell me that you have found a board that is longer than your house is wide, the alarm in that statement depends entirely on how confident you are in your measurement of the house. Maybe the board really is too long, or maybe you measured the house wrong, or maybe your tape measure is faulty. You cannot know which until you examine not just the board, but the whole apparatus of measurement. The galaxies are the board, the age of the universe is the house, and before we accuse the board of being impossible, intellectual honesty demands that we turn around and ask, with real care, how we measured the house. How do we know the universe is 13.8 billion years old? Where does that number actually come from? That is the question that holds everything else up, and it is the one we turn to now. Part 6. how we know how old the universe is. The age of the universe is not a guess, and it is not a tradition. It is a measurement, and like all good measurements, it comes from more than one independent direction, with the directions agreeing. To trust it, or to know exactly how far to trust it, you have to see where it comes from, and the cleanest place to start is with the single most important source of light in all of cosmology, a glow that fills the entire sky in every direction, left over from the moment the universe first became transparent. For the first few 100,000 years after the Big Bang, the cosmos was too hot to be clear. It was a dense, glowing fog of charged particles, electrons, and bare atomic nuclei, and light could not travel freely through it. A photon would move a tiny distance and immediately collide with a charged particle and scatter away, the way light cannot pass through the inside of the sun. The universe was opaque, a wall of fog glowing with heat. Then, about 380,000 years after the beginning, the universe cooled enough for the electrons and nuclei to join into neutral atoms. The fog cleared. Suddenly, light could travel in straight lines across space, and it has been travelling ever since. That released light still surrounds us. We call it the cosmic microwave background, and it is the oldest light there is, a photograph of the universe at the instant it became transparent. That ancient light is the foundation of the cosmic clock. Over the more than 13 billion years since it was released, the expansion of the universe has stretched it, cooling it from the fierce glow of the early fog down to a faint whisper of microwaves, just a few degrees above absolute zero, filling all of space. When we map that glow across the whole sky, we find it is almost perfectly smooth, the same temperature in every direction to about 1 part in 100,000. But not quite perfectly. There are tiny variations, faint patches very slightly hotter and cooler than the average, and those patches are not random noise. They are the imprint of the sound waves that rippled through the hot early universe, frozen into the sky at the moment the fog cleared. The sizes and spacings of those patches encode an enormous amount of information about the contents and history of the cosmos. In the early 2010s, a spacecraft called Planck mapped that ancient glow with exquisite precision, measuring the pattern of hot and cold patches across the entire sky. From that pattern, cosmologists could read off the fundamental properties of the universe. They could read how much ordinary matter it contains, how much dark matter, how much of the mysterious dark energy that drives the expansion, and crucially, how fast the universe is expanding and how that expansion has changed over time. And from all of those together, run backward through the equations that describe an expanding cosmos, they could compute how long it has been since the beginning. The number that came out was 13.79 billion years, with an uncertainty of only about 20 million years. That is a precision of roughly 1 part in 700. The age of the universe from this single line of evidence is known to better than 1%. That alone would be impressive, but the age does not rest on the ancient light alone. It is corroborated from completely separate directions, and the corroboration is what turns a measurement into a fact. Consider the oldest stars. Astronomers can estimate the ages of certain stars from the physics of how they burn, and the most ancient stars we find, in the oldest clusters orbiting our galaxy, come out at around 13 billion years, comfortably younger than the cosmic age from the background light, as they must be. Consider the abundance of the lightest elements. The amounts of hydrogen, helium, and lithium produced in the first few minutes of the universe depend on conditions in those first minutes, and the measured amounts match the predictions of a universe of just this age and composition. Consider the way galaxies cluster across the sky, the way the expansion has accelerated, the cooling of the background glow itself. Every independent line points to the same era. The universe is something close to 13.8 billion years old, and a great many separate measurements agree. It helps to lay the whole timeline out as a single calendar, the way you might spread a year across a wall, because the proportions are the thing that matters, and they are hard to hold in the abstract. Imagine the entire history of the universe compressed into 1 year, the Big Bang at the first instant of the 1st of January, and this present moment at the last stroke of midnight on the 31st of December. On that calendar, the ancient background glow is released within the first few hours of New Year's Day, while the cosmos is still a newborn fog. The cosmic dark ages, the long starless night, fill the rest of that first day. The first stars flicker on sometime in the small hours of the 2nd of January. And the galaxies that frighten us, the ones seen at a few 100 million years, belong to the first week of January, when the year has barely begun. Our own sun does not form until late summer, in early September on this scale. All of recorded human history occupies the final fraction of the final second before midnight. Place the impossible galaxies on that calendar, and you can feel the precise shape of the problem. They are objects from the first few days of January that appear to have the heft and polish of structures that should not exist until at least the spring. It is not that they are old in absolute terms. They are, by the calendar, extraordinarily young, among the very first things the universe made. The trouble is that they look further along in their development than their place in the first week should allow, as if a building begun on the 3rd of January were already weathered and settled and full, the way you would only expect of something raised over many months. The calendar does not soften the puzzle, it sharpens it, by making unmistakable how little time these objects had been given before their light set out toward us. Now, to read the galaxies against this clock, we need one more tool, the relationship between redshift and time. We have said that the expansion of the universe stretches light, and that the more distant the source, the more its light is stretched. That stretching is measured by a number called the redshift, and the redshift maps directly onto how far back in time we are seeing. A modest redshift means recent light. A large redshift means ancient light, from early in cosmic history. The universe breaker galaxies sat at redshifts of roughly 7 to 10, which corresponds to a time between about 500 and 700 million years after the beginning. The record holder at the edge of time sat at a redshift of about 14, which corresponds to roughly 290 million years after the beginning. These are not vague impressions of distance. They are specific points on a well-calibrated timeline, and that is exactly why the objects could be called impossible with such confidence. We knew, with real precision, how little time they had been given. I want to linger on one of those corroborating measurements, because it is among the most beautiful confirmations in all of science, and it reaches back even further than the ancient glow. In the first few minutes after the Big Bang, the entire universe was hot and dense enough to act as a nuclear furnace. In that brief window, before expansion cooled everything below the threshold for fusion, protons and neutrons fused together to make the lightest elements, the hydrogen and helium, and the faint trace of lithium that still fill the cosmos. The exact proportions of those elements depend with great sensitivity on the conditions in those first minutes, on how fast the universe was expanding and how much ordinary matter it contained. Work out the predictions, then go and measure the actual proportions of hydrogen and helium in the most pristine gas we can find, and the two agree to remarkable precision. That agreement is a measurement of the first 3 minutes of the universe, and it fits seamlessly with the age and composition read from the ancient glow, released hundreds of thousands of years later. Two completely different epochs, measured by completely different means, tell the same story. Then there is the cosmic distance ladder, the painstaking chain of measurements that lets us gauge distances across the universe, rung by rung. We begin nearby, with the geometry of stars whose distances we can triangulate directly as the Earth swings around the Sun. We use those to calibrate certain pulsing stars whose brightness reveals their distance, and we use those pulsing stars in turn to calibrate the exploding stars bright enough to be seen across billions of light years. Each rung is checked against the one below it. This ladder is how we measure the expansion in the nearby universe, and it is independent of the ancient glow entirely. The point of walking through all of this is not to drown you in methods. It is to make one thing unmistakable. The age of the universe is not a single fragile reading that could collapse if one instrument failed. It is a conclusion braced from many directions at once, by the first 3 minutes, and by the ancient glow, and by the oldest stars, and by the distance ladder, all leaning on one another, all agreeing. So the ruler is good. This is the crucial thing to absorb because it cuts against the easy reaction. When you first hear that astronomers found galaxies older than the universe, the tempting response is to assume they simply do not know how old the universe is, that the number is soft and they're confused. The opposite is true. The age of the universe is one of the best measured quantities in all of science, pinned down to better than 1%, confirmed from several independent directions that have no reason to agree unless they are all tracking something real. The clock is not the weak link, and that is what makes the galaxies genuinely interesting rather than merely a mistake. They are not pressing against a number we hold loosely. They are pressing against one of the most solid numbers we have, which sharpens the question rather than dissolving it. If the clock is this reliable, and the galaxies still look too old for it, then the trouble must lie somewhere other than the clock. It must lie in our story of what the universe did with the time the clock measures, in our theory of how galaxies are built and how fast they can be built. To see why the galaxies are so troubling, we now have to understand exactly what the Standard Model predicts about the construction of galaxies, and why it insists, with real force, that something as heavy and mature as a universe breaker simply should not be able to exist so soon after the beginning. We have to understand the speed limit on creation itself. Part 7. Why none of this should be possible. To feel the force of the problem, you have to understand the standard story of how a galaxy gets built, because that story contains a speed limit, and the speed limit is what these galaxies seem to be breaking. The story is called hierarchical structure formation, which is a heavy phrase for a simple and rather beautiful idea. The idea is that everything large in the universe was assembled from things smaller, from the bottom up gradually, by gravity, over an enormous span of time. Go back to the beginning, to the universe as the ancient background light reveals it. At that moment, the cosmos was almost perfectly smooth, the same in every direction to about 1 part in 100,000. Almost, but not quite. There were those faint variations, regions very slightly denser than average, and regions very slightly thinner. Those tiny differences were the seeds of everything. In a region slightly denser than its surroundings, gravity is slightly stronger, so it pulls in matter from nearby a little more effectively. As it gathers matter, it becomes denser still, which makes its gravity stronger still, which lets it gather even more. The process feeds on itself. Over time, the slightly dense regions grow into clearly dense regions, and the slightly thin regions are drained and become true voids. The smooth early universe slowly curdles into clumps and gaps. The first things to collapse in this picture are small. Gravity acts fastest on small scales, where matter does not have far to travel to gather. So the universe builds its structure in a particular order. First come small clumps of dark matter, the invisible material that makes up most of the mass and provides the gravitational scaffolding for everything else. Ordinary gas falls into those clumps, and where the gas grows dense and cold enough, it collapses further and ignites the first stars. Small galaxies form first. Then those small galaxies, pulled by their mutual gravity, fall together and merge into larger ones. Larger galaxies merge into larger still. The great spiral and elliptical galaxies of today, in this story, are not original. They are the accumulated result of countless mergers, built up piece by piece over billions of years from the small seeds that came first. It is a process of assembly, and assembly takes time. That time is the crux. Because structure builds from the bottom up, and because gravity needs time to do its gathering against the expansion of space that is constantly pulling matter apart, there is a hard limit on how much can have collapsed into any one place by any given moment. Run the equations forward from the smooth early universe, and you can calculate for any epoch the maximum mass that could plausibly have gathered into a single galaxy by then. Early on, that maximum is small, because there simply has not been enough time for much to come together. The ceiling rises as the universe ages and more matter has time to fall into the growing clumps. But in the first few 100 million years, the ceiling is low. There should be only modest objects, the small seeds still in the early stages of assembly. The universe breaker galaxies pressed against that ceiling, and in the most extreme readings appeared to lift right through it. To contain as many stars as they seem to contain, so early, they would have needed to gather essentially all of the ordinary matter available in their region and convert nearly every atom of it into stars with almost perfect efficiency. And that second part, the efficiency, is its own impossibility, because the universe is never efficient at making stars. Real galaxies, everywhere we look, are wasteful. They turn only a small fraction of their available gas into stars, because the moment stars begin to form, they fight back against further star formation. Young massive stars pour out radiation and fierce winds, and when they die, they explode as supernovae, and all of that energy heats the surrounding gas and blows it apart, scattering the raw material before most of it can collapse. Star formation, in the real universe, is a process that keeps interrupting itself. A galaxy that turned nearly all of its gas into stars would have to have somehow switched off that self-interruption entirely, running the furnace wide open with nothing pushing back. So the demand these galaxies placed on the theory was double. They needed to have gathered too much matter too fast, beating the speed limit set by gravity and the expansion of space, and they needed to have converted that matter into stars with an efficiency the universe never shows, beating the self-regulation that makes real galaxies wasteful. Either demand alone would be hard. Both together, in the first few percent of cosmic history, looked impossible. That is the technical content behind the headline. Not a vague sense that the galaxies were surprising, but a specific quantifiable collision between what the standard model permits and what the data seem to show. There is a piece of this picture that deserves its own moment, because without it none of the rest works, and it is the part most people never hear about. The galaxies we see, all their stars and gas, are only a small fraction of the matter in the universe. The great majority of the matter is dark, invisible, detectable only by its gravity, and it is the true scaffolding on which everything visible is built. When we say structure grows from the bottom up, we are really describing the dark matter first. The dark matter, feeling only gravity and not the pressure that slows ordinary gas, begins gathering into clumps early, building an invisible web of dense knots and connecting filaments threaded through all of space. Only afterward does the ordinary gas, the stuff that can actually shine, fall into the gravitational wells the dark matter has already dug. The visible universe is a thin tracing of light laid over a hidden framework of darkness, and the framework came first. That ordering sets the pace of everything. A galaxy cannot gather more ordinary matter than the dark matter well beneath it can hold, and the wells themselves take time to grow as the invisible web slowly tightens. So when we calculate the ceiling on how massive an early galaxy can be, we are really calculating how far the dark matter wells could have sunk by that early time, and how much ordinary gas could have pooled at their bottoms, and how much of that gas could have turned to stars. Every step in that chain has a speed limit, and the speed limits compound. This is why the universe breakers struck at something fundamental. They did not merely strain our model of stars. They strained the whole nested picture, the dark scaffolding and the gas that fills it, and the stars that light it, all of which is supposed to assemble in a slow and orderly sequence. To break the timeline of the galaxies is to question the timeline of the invisible web beneath them, and that web is woven from the same physics that fits everything else we measure. I want to pause here in a slower register, because we have been climbing through a fair amount of physics, and this is a good place to let it settle, the way the night itself settles around a long thought. Picture the early universe not as a diagram but as a place. Imagine the darkness after the background light was released, before the first stars, a span astronomers call the cosmic dark ages. The cosmos is filled with a smooth, dim haze of hydrogen and helium gas, cooling slowly, lit by nothing, drifting in the gentle pull of the unseen dark matter beneath it. It is quiet there, and patient, and almost featureless. Then, very slowly, the gas begins to gather toward the densest knots of the dark matter scaffolding. It flows inward over millions of years, thickening, cooling, sinking toward the centers of the invisible wells. And somewhere in the heart of the densest knot, the gas grows so dense and so cold that it can no longer hold itself up, and it collapses, and the first star ignites, and a single point of light appears in a universe that has never known one. That is the slow, patient, bottom-up beginning the standard model describes. It is gradual by its very nature. It does not rush. And that is exactly why the universe breakers were so disturbing. They did not look gradual. They looked rushed, as though the patient process I just described had somehow been run at many times its proper speed, building grand, heavy, mature galaxies in the time the theory had allotted for the very first small seeds. The collision was real, and it was sharp, and in early 2023 no one could say for certain how it would be resolved. The standard model had been right about so much, confirmed from so many directions, that the idea of it failing here was genuinely frightening to contemplate. And yet, frightening as it was, there was a reason not to panic, a reason rooted not in any particular calculation, but in the history of the science itself. Because this was not the first time astronomers had stared at the sky and found something that seemed to be older than the universe that held it. It had happened before, within living memory, in a crisis that felt at the time every bit as severe as this one. And the way that earlier crisis resolved is the most useful thing we possess for thinking clearly about this one. So let's go back just a few decades to the last time the cosmos seemed to contain something older than itself. Part 8. The Crisis That Came Before. In the 1990s, astronomers had a problem that sounds eerily familiar. The oldest stars in the galaxy appeared to be older than the universe. Not a few stars at the edge of the observable cosmos, but the ancient stars in our own cosmic backyard, The stars in the globular clusters, those tight, beautiful swarms of hundreds of thousands of suns that orbit the Milky Way like a halo of old lanterns. When astronomers calculated the ages of those stars, the numbers came out larger than the age the universe was thought to have at the time. The container appeared to be younger than its contents. It was the same impossibility in a different costume. To see how that happened, you need to know that the ages of stars and the age of the universe were being measured by completely separate methods, and the two methods were quarrelling. The ages of the oldest stars came from stellar physics, from a detailed understanding of how a star burns its fuel and changes over time. Astronomers can model the life of a star with real confidence. They know how brightly a star of a given mass shines, how it evolves as it exhausts the hydrogen in its core, how it swells and changes colour in its old age. By looking at which stars in a globular cluster have already begun to age and which have not, astronomers can read the cluster's age the way you might estimate the age of a forest from which trees have started to fall. Those readings, in the 90s, gave ages for the oldest clusters of perhaps 15 or 16 billion years. The age of the universe, meanwhile, came from the expansion. If you measure how fast the universe is expanding today, you can run the expansion backward to estimate how long ago everything was together at the beginning. But that calculation depends critically on the measured expansion rate, and in the 90s, the expansion rate was poorly known and hotly disputed. Different teams using different methods got different values, and the disagreement was bitter. Depending on which value you believed, the universe came out somewhere between about 10 and 20 billion years old. And for a good portion of that range, the universe was younger than the 15 or 16 billion-year-old stars it was supposed to contain. The stars were older than their own cosmos. Let me put you beside one of the people wrestling with this, because it is the same human moment we have already lived once tonight, repeating across the decades. Picture an astronomer at a chalkboard or hunched over an early computer, working through the age of a globular cluster. The stellar physics is solid, the model is trusted, the number it produces is 15, maybe 16 billion years, and on the other side of the board sits the age of the universe, derived from the expansion, and depending on the day and the measurement, it might be 12 billion or 10. The astronomer stares at the two numbers, the star older than the sky that holds it, and feels exactly the vertigo we described before. Something is wrong. The numbers cannot both be right, but every individual step in each calculation looks sound. There is no obvious error to point to, no single mistake to cross out. There is only the quiet, stubborn contradiction, the same kind of number that will not go away. It is the 1990s, and the universe appears to contain something older than itself, and no one yet knows why. It is worth understanding why the expansion rate was so badly known back then, because it shows that even our finest numbers have humble and contested histories. For much of the late 20th century, the measurement of the expansion rate was the subject of a long and famously bitter feud between rival camps of astronomers. One camp, working with one set of methods and assumptions, consistently arrived at a slow expansion, which implied an old and roomy universe. The other camp, using different calibrations, consistently arrived at a fast expansion, which implied a young and cramped one. The two answers differed by nearly a factor of 2, and the disagreement ran for decades, conducted at conferences and in journals with real heat behind it, because the stakes were nothing less than the age and size of everything. The age of the universe was not a fixed and trusted number handed down from on high. It was a moving target, fought over by serious people who could not yet make their instruments precise enough to settle the matter. In that environment, the apparent paradox of the old stars was almost inevitable. If the universe might be as young as 10 or 12 billion years, and the oldest stars came out at 15 or 16, then for one whole side of the expansion feud, the stars were plainly older than the cosmos. The contradiction was not a sign that physics had failed. It was a sign that the expansion rate was still genuinely uncertain, still being fought over, and that one of the warring numbers had to be wrong. The resolution, when it came, did not crown either camp the outright winner. It split the difference and added a piece neither side had fully anticipated: the accelerating expansion driven by dark energy, which reshaped the whole calculation. The decades of bitter argument were not wasted. They were the long, necessary grinding of a measurement toward precision, and the paradox of the old stars was simply a symptom of that grinding visible while the work was still unfinished. Now here is the part that matters, the part that should change how you feel about the galaxies at the edge of time. That earlier crisis did not resolve by overturning physics. It did not resolve by discovering that stars can be older than the universe, because of course they cannot. It resolved, quietly and from two directions at once, by improving the measurements. First, a satellite called Hipparcos measured the distances to stars far more precisely than had ever been done before, and better distances meant better brightnesses, and better brightnesses meant the ages of the oldest stars came down somewhat from the alarming highs. The stars were a little younger than the worst estimates had said. And second, at the very end of the 90s, astronomers discovered that the expansion of the universe is accelerating, driven by the dark energy we now know pervades space. That discovery changed the calculation of the cosmic age, and when the new physics was folded in, the age of the universe settled at a larger and more comfortable value, around 13.8 billion years. The two numbers, the age of the stars and the age of the universe, slid past each other into their proper order. The stars were old, but the universe was older, as it had to be. The crisis evaporated. Sit with what actually happened there, because it is the lesson the whole night has been building toward. Two carefully made measurements disagreed, and the disagreement was sharp, and for years it looked like a genuine paradox that might force a revolution in physics. And in the end it was not a paradox at all. It was two rulers that had not yet been made precise enough, measuring the same stretch of reality and getting answers that did not quite line up. When both rulers were sharpened, the answers came into agreement, and in the process, the sharpening taught us something profound that we had not known before: the existence of dark energy, the accelerating expansion, a whole missing piece of the cosmos. The apparent contradiction was not a wall, it was a door. The discomfort was not the universe breaking. It was the universe handing us a correction, and the correction contained a discovery. That is the most valuable thing you can carry into your thinking about the galaxies that frighten astronomers today. The phrase older than the universe has been spoken before, in full seriousness, by careful people who could not immediately explain what they were seeing, and it turned out not to mean what it literally said. It turned out to mean that two of our measurements disagreed, and that the disagreement was about to make us smarter. The fear was real, and it was honest, and it was also, in the end, the most productive thing that could have happened, because it forced the measurements to improve and revealed a piece of reality we had been missing. The thing that felt like the ground collapsing was actually the universe correcting us, and the correction was a gift. The story has a single star at its centre that makes the whole pattern personal, and its name has become a kind of legend. There is a star not far from us as cosmic distances go, only about 190 light-years away, that astronomers nicknamed the Methuselah star after the longest-lived figure in old scripture. It is one of the oldest stars we have ever found, a pristine relic from the early universe drifting through our own galactic neighbourhood. And when astronomers first measured its age with care around 2013, the number that came back was about 14.5 billion years. The universe by then was understood to be about 13.8 billion years old. The star appeared to be older than the cosmos by the better part of 1 billion years. The legend of the star that predates the universe was born, and it spread far beyond astronomy, into the kind of headline that delights anyone who enjoys watching the experts squirm. But look at what happened next, because it is the same pattern we've seen all night, played out in miniature on a single star. The age estimate carried an uncertainty, a margin of error of perhaps 800 million years in either direction, which meant that even the original measurement was only barely in tension with the age of the universe, within a hair of being consistent once you accounted for the wiggle room, and then the measurement improved. Astronomers refined the star's distance, reconsidered its chemistry, sharpened the models of how it burns, and the age came down, settling to something comfortably younger than the universe, around 13.7 billion years or even less, depending on the analysis. The star was old, genuinely ancient, one of the first generation to light up after the beginning. But it was not older than the universe. It never had been. It had only looked that way for as long as our measurement was not yet sharp enough, and when the measurement sharpened, the impossibility quietly dissolved, exactly as it always does. So when Webb showed us galaxies that look too old, too heavy, too developed for their place in time, we are not standing somewhere new. We are standing somewhere we have stood before, and we know, from experience, the shape of how it tends to resolve. It tends to resolve by finding that one of our measurements, or one of our assumptions, was not yet sharp enough, and that is exactly the direction the work has gone since 2023. The first and strongest crack in the impossibility came from realizing that the light from these galaxies might not be telling us what we thought it was telling us. The light, it turned out, might have been lying to us in a very particular and very interesting way. To understand how, we have to look at what else, besides stars, can make a distant object blaze. Part 9. The light was lying. When astronomers measure the mass of a distant galaxy, they are really measuring its light, and then translating that light into a number of stars. The translation rests on an assumption so natural that it is easy to forget it is an assumption at all. The assumption is that the light comes from stars. You see a bright object in the early universe, you assume the brightness is starlight, and you reason backward to how many stars it would take to produce that much glow. The more light, the more stars, the more mass. That chain of reasoning is how the universe breakers were weighed, and it is sound, as long as the founding assumption holds. But there is something else in the universe that can pour out staggering quantities of light, something that is not made of stars at all. And if that something is present, the whole chain of reasoning bends. The something is a feeding black hole. A black hole itself emits nothing. That is what makes it a black hole. But when a black hole is actively swallowing matter, the matter does not fall in quietly. It spirals inward through a flattened disk, and in that disk it is compressed and sheared and heated by friction to ferocious temperatures until the gas is glowing white hot and pouring out radiation across the spectrum. A supermassive black hole in the middle of a galaxy, feeding hungrily, can outshine all the stars of that galaxy combined. We have known this for a long time. The brilliant beacons we call quasars are exactly this. The glow of matter being devoured by giant black holes in the centres of distant galaxies, blazing so brightly we can see them across most of the observable universe. The light of a feeding black hole is some of the most intense light there is, and it is not starlight. Now carry that into the problem of the impossible galaxies. Suppose one of these compact red objects is not simply a galaxy stuffed with an impossible number of stars. Suppose a good fraction of its light comes from a growing black hole at its centre, feeding on gas and blazing. If you do not know the black hole is there, you will attribute all of that light to stars, and you will conclude the object contains far more stars and far more mass than it actually does. The black hole is doing some of the shining, but you are crediting all of it to the stellar population. Your mass estimate balloons. The galaxy looks impossibly heavy, not because it truly is, but because you have mistaken the light of a black hole for the light of 100 billion suns. This is the resolution that did the most to dissolve the crisis, and by 2024 the evidence for it was mounting fast. When astronomers obtained better data on the most extreme early objects, spreading their light into spectra rather than relying on a few broad colours, they began to find the telltale signatures of feeding black holes hiding inside them. The light was contaminated, in the technical sense, by an accreting black hole that the photometry alone could not reveal. And when that contribution was accounted for, the inferred stellar masses came down, often dramatically. The galaxies that had seemed to contain as many stars as the Milky Way turned out to contain far fewer, with the surplus light explained by the black hole rather than by an impossible host of stars. One widely circulated summary of the new work put it with a kind of relief, that the early galaxies were not too big for their britches after all. The black holes had been padding the numbers. These contaminated objects acquired a name that has become one of the signatures of the whole Webb era. They are called the little red dots. They are compact. They are strikingly red, and they appear in surprising abundance in the early universe, and untangling exactly what they are has become one of the central puzzles of modern astronomy. Many of them show the marks of a feeding black hole at the core, and the black holes appear to be startlingly large relative to the stars around them. In the universe nearby, there is a fairly steady relationship between the mass of a galaxy's central black hole and the mass of the galaxy's stars, with the black hole typically holding a tiny fraction, around 0.1%, of the stellar mass. In some of these little red dots, the ratio is wildly different. The black hole appears to hold a substantial fraction of the whole, in some cases more than 30%. These are objects where the black hole is not a small dark heart inside a great body of stars, but a dominant engine that rivals or exceeds the stars themselves. That raises its own hard question, of course, because a black hole that large, that early, is its own kind of puzzle. How do you grow a black hole holding millions of times the mass of the Sun in only a few 100 million years? The answer probably involves seeds that started large, Perhaps the direct collapse of enormous clouds of gas into black holes without ever forming stars first, and then growth at or beyond the normal speed limit, the rate at which the outward pressure of a black hole's own radiation is supposed to choke off its feeding. These are active areas of research, and they are genuinely unsolved. But notice what has happened to the original crisis. The impossibility of the galaxies, the part that threatened to break cosmology, has largely transformed into a different and more tractable puzzle about how black holes grow. The threat to the age of the universe has eased. What remains is a hard but ordinary astrophysical question, the kind the field knows how to chew on. This is the moment to bring back a phrase we left hanging. When the universe breakers were announced, the line that captured the feeling was that the astronomers had discovered the impossible. And for a year or two, that is exactly what it looked like. But the impossible has a way of turning possible the moment you understand what you are actually looking at. The galaxies were not impossible, they were misread. The light that seemed to demand an impossible number of stars was partly the light of black holes, and once that was understood, the galaxies settled back within the bounds of what the universe can build. The word impossible, spoken in honest alarm, turned out to mean not yet understood, which is a very different and far more hopeful thing. The discovery of the impossible became the discovery that we had not yet learned to read the light. To feel why this explanation is so persuasive, it helps to remember just how absurdly luminous a feeding black hole can be. We have known about these objects for more than half a century, since astronomers first found points of light that looked like ordinary stars but sat at staggering distances, which meant they had to be pouring out the light of entire galaxies from a region no larger than our solar system. They called them quasi-stellar objects, quasars, and for a while they were among the most baffling things in the sky. We now understand them as the brilliant cores of galaxies where a giant black hole is feeding hard, and a single one can outshine 100 billion stars from a space you could lose inside a single star system. The light does not come from the black hole, which emits nothing. It comes from the doomed matter spiraling in, compressed and heated until, in its final moments before crossing the point of no return, it blazes more brightly than anything else in the cosmos. The brightest steady light in the universe is the light of matter being destroyed. Now place one of those engines, smaller but still ferocious, in the heart of an early galaxy, and you can see how the confusion arose. From across more than 13 billion light-years, that galaxy is an unresolved point, a single smudge. You cannot separate the glow of the central black hole from the glow of the surrounding stars. All you see is the total, and if you assume the total is starlight, you will credit the stars with light that the black hole produced, and your count of stars, and therefore your estimate of mass, will swell far beyond the truth. There is even a natural speed limit on how brightly such a black hole can shine, set by the point where the outward push of its own radiation balances the inward pull of its gravity, and some of these early objects appear to be feeding right at or beyond that limit, blazing as brightly as physics allows. That is precisely the kind of engine that can make a modest galaxy masquerade as a monster. The question of how these black holes got so large so fast is genuinely one of the open frontiers, and it is worth being honest that trading one puzzle for another is not the same as solving everything. To grow a black hole of millions of solar masses within a few 100 million years, you may need to start with an unusually large seed rather than the modest remnant of a single dead star. One leading idea is that enormous clouds of pristine gas collapse directly into black holes early on, skipping the star stage entirely, giving the holes a running head start. Another is that the early holes fed so furiously, in such gas-rich surroundings, that they outran the usual limits on their growth. Both ideas are under active investigation, and neither is settled. But the crucial shift has already happened. The threat that hung over the age of the universe, the fear that the timeline itself might be broken, has been converted into a hard but ordinary problem about how black holes are seeded and fed, the kind of problem astronomy knows how to attack. I do not want to overstate it. The black hole explanation is powerful, and it has done a great deal of the work, but it has not closed every case, and the astrophysics of these early black holes raises new and serious questions of its own. The crisis has softened rather than vanished, but the direction of travel is clear, and it is the same direction the 1990s crisis travelled. A measurement that seemed to break the universe turned out to be a measurement we had not yet learned to interpret correctly. Sharpen the measurement, understand what the light is truly made of, and the impossibility recedes. That is one road out of the problem, and it is the road most of the evidence has taken. But it is not the only road, and the other road is just as interesting, because it asks whether the early universe might simply have been a more vigorous place than we ever imagined, building real stars, real galaxies, faster than our model said it could. To walk that road, we have to go inside one of these galaxies at the height of its making. Part 10, or the universe simply worked faster. There is a second way out of the crisis, and it does not require any hidden black holes at all. It keeps the galaxies made of stars, genuine stars, and instead changes our assumptions about how quickly and how brightly those stars could have been made. This road is, in some ways, the more humbling of the two, because it does not say we misread the light. It says the early universe was a more productive, more furious engine of creation than our models allowed, and that our intuitions about the speed of cosmic construction were simply too slow. Begin with efficiency. We said that real galaxies are wasteful, that they convert only a small fraction of their gas into stars because newborn stars fight back, heating and blowing away the gas before it can collapse. That self-regulation is what keeps star formation slow and steady in the universe we see around us. But the early universe was a different environment. It was denser because everything was packed into a smaller space. The gas was more abundant and more tightly concentrated, and in such conditions, some astronomers have argued, star formation could have run with much less of the usual self-interruption. If the gas is dense enough and collapses fast enough, stars can form in great bursts before their own feedback has time to disperse the surrounding material. The furnace runs wide open, briefly, because the fuel is gathered and ignited faster than the fire can blow it apart. These are sometimes called feedback-free starbursts, and they would let an early galaxy convert its gas into stars far more efficiently than any galaxy nearby, building real stellar mass at a rate our standard assumptions forbid. It is worth understanding why the early universe was such a different place to make stars, because the difference is not a small adjustment but a change of environment. The whole cosmos was younger, and therefore smaller, with everything packed into a fraction of the volume it occupies today. Density scales powerfully with that compression, so the gas in early galaxies was vastly more concentrated than the thin material of the modern universe. A denser cloud of gas collapses faster and more violently under its own gravity, and it can keep collapsing even as the first stars within it begin to shine and push back. In the calm, spread-out galaxies of today, the feedback from young stars easily wins, dispersing the gas and throttling star formation down to the slow trickle we observe. In the dense furnaces of the early universe, gravity may have been winning the race, pulling gas into stars faster than the newborn stars could heat and scatter it. The same physics of star formation, run in a denser and more crowded setting, produces a far more vigorous result. There is a poetic symmetry in realizing that the conditions which make the early galaxies look impossible are the very conditions that explain how they could be real. We expected the early universe to behave like the calm one we know, building stars slowly and wastefully, and against that expectation the galaxies looked impossible. But the early universe was not calm. It was compressed, dense, and turbulent, an environment built for rapid and efficient creation. Once you let go of the assumption that the dawn worked at the same gentle pace as the present, the impossibility begins to dissolve on its own. The galaxies are not too advanced for their time. We simply misjudged what their time was capable of by imagining it in the image of our own quiet era rather than the fierce and crowded one it actually was. Add to that the nature of bursts themselves. Star formation does not have to proceed at a steady rate. It can come in sudden, intense episodes, a galaxy flaring with new stars for a few million years, and then quieting, then flaring again. And here is the subtle point. A galaxy caught in the middle of a burst is far brighter than its long-term average. If you survey the early universe and you happen to catch galaxies during their bursts, you will see them at their most luminous, and you will overcount how many bright galaxies there are, and you will overestimate their masses if you assume the brightness reflects a steady, settled population of stars. Bursty star formation makes the early universe flicker, and a snapshot of a flickering universe catches the flashes and misses the dim intervals between them. Some of the excess brightness that alarmed everyone may simply be the early cosmos caught mid-flash. Then there is the most radical of the stellar explanations, which changes the stars themselves. When stars form, they form in a range of masses, many small ones and a few large ones, and the particular balance of that range is called the initial mass function. In the universe today, that balance favours small stars. For every massive, brilliant star, there are many faint, modest ones. but the first generations of stars formed from gas that was almost pure hydrogen and helium, without the heavier elements that influence how gas cools and fragments. In that pristine gas, some theorists argue, stars may have formed with a different balance, tilted toward the massive end, producing relatively more of the large, hot, brilliant stars, and massive stars are extravagantly bright. A population tilted toward heavy stars would pour out far more light per unit of mass than a normal population. That means the early universe could look much brighter than expected without containing any more total mass than expected. The light is inflated not by black holes, but by an unusual abundance of brilliant stars. Any of these, or all of them together, could ease the brightness problem while leaving the age of the universe completely intact. The galaxies are real, the stars are real, the timeline is unchanged. What changes is our picture of how vigorously the early universe could build, and how brightly it could shine while doing so. And there is something genuinely wonderful in that possibility, a wonder quite different from fear. It suggests that the dawn of the cosmos was not the slow, faint, hesitant affair we imagined, but a time of fierce and rapid creation, galaxies igniting and blazing and assembling themselves with an energy the later universe would never match again. The early universe on this picture was not behind schedule. It was ahead of ours. Let me take you inside one of these galaxies at the height of its making, because this is the kind of moment the whole night has been circling toward, and it is worth dwelling in slowly. Imagine you are suspended within one of these early galaxies, a few 100 million years after the beginning. Around you is gas, hydrogen and helium, denser than anything in the calm galaxies of the later universe, and it is cold, and it is collapsing. Everywhere you look, the gas is sinking inward under its own weight, gathering into knots, and the knots are growing brighter. Stars are igniting all around you, not one at a time over the ages, but in a rush, dozens and hundreds and thousands of them flaring into existence across the galaxy in a span that is brief by cosmic standards. The light builds and builds. Massive blue-white stars blaze into being, far brighter than the sun, living fast and burning hard. The whole galaxy is flushing with light, a furnace at full throttle, converting its abundant gas into stars faster than the newborn stars can blow the remaining gas away. For a few million years, this object shines more brilliantly than it ever will again, a single sustained flash of creation near the dawn of time. You're watching a galaxy being born not slowly but all at once, in a burst of making so intense it lit up the early universe brightly enough that, more than 13 billion years later, a gold mirror in the cold would catch its glow, and a species would argue about whether it should have been allowed to exist. That is the second road out of the crisis, and notice that it leads to wonder rather than terror. On this reading, the galaxies are not breaking the universe. They are revealing that the universe, in its youth, was capable of building faster and shining harder than we ever gave it credit for. Our models were too timid. The cosmos was bolder, and the appropriate response to that is not fear, but a kind of delight. The delight of discovering that the thing you study is grander and more capable than you assumed. The early universe was a more powerful engine of creation than the textbooks described, and Webb caught it in the act. There is a reason to think the very first stars really were different, and it comes straight from the chemistry we have already discussed. The stars forming today are born from gas that has been salted by previous generations, gas that carries carbon and oxygen and iron scattered by the deaths of earlier stars. Those heavier elements matter enormously to how a cloud of gas collapses, because they help the gas shed its heat and cool down. Cooling lets a cloud fragment into many small pieces, and many small pieces become many small stars. But the very first clouds had none of that seasoning. They were almost pure hydrogen and helium, and pure hydrogen and helium cool poorly. A cloud that cannot cool efficiently does not fragment into many small pieces. It tends to collapse into a few enormous ones. So the first stars, the truly pristine generation, are thought to have been giants, far more massive than the sun, blindingly bright and very short-lived, burning through their fuel in a cosmic eye blink and dying in tremendous explosions that seeded the next generation with the first heavy elements. If the earliest galaxies were lit by an unusual abundance of such giant stars, they would have blazed far out of proportion to their mass, which is exactly what the brightness problem seems to require. And those same giant stars, dying quickly, would have enriched their galaxies with heavy elements with astonishing speed, which is exactly what the early oxygen seems to show. Notice how the pieces begin to fit together. A top-heavy first generation explains both the excess light and the premature chemistry at once, without any need to touch the age of the universe. The early cosmos, on this reading, was not breaking the rules. It was running an opening chapter we had simply never seen up close before, a chapter written in stars larger and fiercer than any that survived to burn in the calm galaxies around us today. Hold both roads in your mind together, because the honest truth is that the resolution is probably not one or the other, but some braid of all of it. Some of the apparent mass is black hole light wearing the costume of stars. Some of the apparent brightness is the early universe building stars more efficiently than the later universe ever would. Some is the flicker of bursts caught at their peak. Some is the extravagant glare of a first generation of giants. No single explanation has to carry the whole weight, and the most likely outcome is that several of them share the load, each shaving a piece off the impossibility until what remains is a universe that was merely surprising rather than broken. That is how most great anomalies actually resolve, not with one clean revelation, but with a gradual accumulation of partial answers that, together, dissolve the original shock. Between these two roads, the hidden black holes and the faster, brighter star formation, most of the impossibility has been absorbed. The galaxies are heavy partly because we mistook black hole light for starlight, and bright partly because the early universe built stars more efficiently and more brilliantly than we knew. Neither road requires us to tear up the age of the universe or rewrite the foundations of cosmology. Both keep 13.8 billion years intact and instead revise our picture of what happened within those years. The crisis, in other words, has been substantially tamed, and yet, if I am to be honest with you, and the channel is always honest with you, the story does not close with a perfectly tidy bow. There remains a crack in our timekeeping that these explanations do not touch, an independent disagreement that has nothing to do with early galaxies and everything to do with how confident we should be in our cosmic clock. To see why the matter is not entirely settled, we have to look at a second, separate tension that has been quietly troubling cosmologists for years. Part 11. The Crack That Will Not Close. The early galaxies are not the only place where our measurement of cosmic time refuses to sit perfectly still. There is a second tension, entirely independent of Webb, that has been growing sharper for more than a decade, and it concerns the most basic number in all of cosmology, the rate at which the universe is expanding. That rate is the foundation of the cosmic clock. It is what we run backward to find the age of the universe in the first place, and right now we have two excellent ways of measuring it, and they do not agree. The first way uses the ancient background light, the relic glow from when the universe became transparent. From the precise pattern of hot and cold patches in that glow, cosmologists can derive the expansion rate of the early universe and project it forward, and the answer comes out at about 67 kilometers per second per megaparsec. The number itself is less important than what it represents, a particular speed of cosmic expansion, measured from the universe's infancy with great precision. The second way works in the opposite direction, from the present outward. Astronomers measure the distances and recession speeds of relatively nearby objects, using stars of known brightness and exploding stars called supernovae as cosmic mileposts, and from those they read the expansion rate directly in the modern universe. And that method gives a noticeably higher number, around 73. Those two numbers should be the same. They are measuring the same universe, the same expansion, by two roots, and the roots should meet in the middle. Instead, they disagree by an amount far larger than the uncertainties in either measurement. The disagreement has a name. It is called the Hubble tension, and it has resisted resolution for years, surviving every attempt to blame it on a hidden error in one method or the other. Both measurements have been checked and rechecked and refined, and the gap has stubbornly remained, even widened. It now sits at a level of statistical significance that, in physics, is generally treated as the threshold for taking a discrepancy very seriously indeed. Something, somewhere, in our understanding of the universe's expansion is not complete. And here is why it matters for our story tonight. The expansion rate is exactly what sets the age of the universe. A faster expansion rate implies a younger universe, because if everything is flying apart more quickly now, then less time was needed to reach the present spread from the initial togetherness. The early universe measurement, the lower number, gives the comfortable 13.8 billion years. But the local measurement, the higher number, taken on its own, would imply a somewhat younger universe, with less time on the clock. The two cracks in our timekeeping, the early galaxies that look too old and the expansion rate that will not agree with itself, are not the same problem, and there is no established connection between them, but they share a flavour. Both are the universe quietly insisting that our measurement of cosmic time is not yet perfectly settled, that the most basic numbers still have room to move. I introduced a phrase early on, and now is the moment to return to it. I said that whenever the clock and the story disagree, one of them is about to be corrected. We established the clock with care, the 13.8 billion years from the ancient light, and we found it trustworthy, pinned down to better than 1%, confirmed from several directions. But the Hubble tension is a reminder that even a clock measured to better than 1% is still a measurement, not a commandment. It still has the capacity to surprise us. The age of the universe is not handed down from on high. It is read off the sky by careful people using imperfect instruments, and the reading can shift as the instruments improve. The clock is excellent. The clock is also, like all measurements, provisional. Holding both of those truths at once is what intellectual honesty requires. It is worth understanding why this particular disagreement has proven so stubborn, because its stubbornness is what makes it interesting. When two measurements of the same quantity disagree, the usual culprit is a hidden error in one of them, some overlooked complication that, once found and corrected, brings the two into line. For years, that is what most cosmologists expected would happen with the expansion rate. They assumed someone would eventually find the flaw, the miscalibrated rung on the distance ladder or the subtle systematic in the ancient glow, and the gap would close. But the harder people looked, the more both measurements held their ground. The teams measuring the nearby expansion checked their pulsing stars and their exploding stars against independent methods, and the high number stayed high. The teams reading the ancient glow refined their analysis, and the low number stayed low. The gap did not shrink under scrutiny. If anything, it grew more solid, until the disagreement reached a level of significance that, in physics, is the threshold for calling something a genuine discovery rather than a fluke. What that persistence suggests is unsettling in a productive way. It hints that the disagreement may not be an error at all, but a real feature of the universe, a sign that something is missing from our model of how the cosmos expanded between the early time the ancient glow records and the late time the nearby measurements probe. Some researchers have proposed that a burst of additional dark energy in the early universe could bridge the gap, subtly changing the early expansion in a way that reconciles the two numbers. Others have looked to new properties of the mysterious dark sector, or to physics we have not yet discovered. None of these proposals has won the field, and the matter remains genuinely open. But the very existence of the tension, sitting beside the early galaxy puzzle, is the second reason we cannot quite declare our timekeeping finished. Two independent measurements, the galaxies and the expansion rate, are both whispering the same gentle warning that the most basic numbers of cosmology still have a little room left to move. This is the soil in which the fringe ideas grow, and we should walk through them honestly, because the channel does not pretend they do not exist. The most dramatic claim, repeated endlessly online, is that Webb's galaxies have disproven the Big Bang outright, that the whole expanding universe picture is wrong, and we should return to older notions of a static, unchanging cosmos. This claim does not survive contact with the full body of evidence, and it is important to say so plainly. The very redshifts that place these galaxies in the early universe are themselves a consequence of cosmic expansion. The stretching of their light is the expansion made visible, and the ancient background glow, the relic of the hot early universe, simply has no good explanation in a static, eternal cosmos. A universe that was always the same would not have a leftover warmth from a hotter beginning, because it would have had no hotter beginning. What Webb strained was the timing of how galaxies assembled within the expanding universe, not the fact of the expansion itself. The Big Bang framework absorbed the shock and remained standing. A subtler proposal, made by a serious researcher and worth mentioning fairly, suggested that the universe might be far older than we think, perhaps around twice the accepted age, which would hand the early galaxies all the time they could possibly need. It is a real idea, published in a real journal. But it comes at a steep price. To work, it requires reviving the old notion of tired light, the idea that light loses energy as it travels for reasons other than expansion, combined with the assumption that the fundamental constants of physics slowly change over cosmic time. The mainstream rejects these ingredients, not out of stubbornness, but because they conflict with a great deal of other tightly measured data. You cannot adopt them to rescue the galaxies without breaking other things that are even better established. It is a rescue that costs more than it saves, which is why it remains a fringe position rather than a consensus, even as the galaxies push the field to consider almost everything. It is worth being gentle about why these rescues are so appealing, because the appeal is human and understandable even when the ideas do not hold. There is a real thrill in the thought that the experts have it all wrong, that the official story is a house of cards and a lone outsider has seen through it. That thrill is not foolish. The history of science does contain moments when a consensus was overturned by an unexpected result, and those moments are rightly celebrated. The trouble is that for every consensus that fell, there were countless dramatic claims of overthrow that simply did not survive scrutiny, and telling the two apart requires looking at the whole body of evidence rather than the single exciting anomaly. A good idea has to explain not just the one thing that excites you, but everything that was already explained. The expanding universe picture explains the ancient glow, the proportions of the lightest elements, the way galaxies recede in proportion to their distance, and a dozen other measurements besides. Any replacement has to account for all of that, and the rescues on offer cannot. They solve the early galaxies by breaking something better established, which is not a solution at all but a trade of a small puzzle for a larger one. And then there is the suspicion that hovers behind all of these claims, the idea that the experts are hiding a crisis, quietly covering up the fact that cosmology is broken. This one collapses the instant you look at how the whole episode actually unfolded, because the opposite is true in every detail. The tension was not hidden. It was announced by the discoverers themselves in the most prominent journals in science in real time, with the word impossible attached and a press tour to amplify it. Cosmologists did not bury the anomaly. They competed to publish it, to explain it, to be the one who cracked it. A hidden crisis does not arrive as a magazine cover in a worldwide news cycle. The argument over these galaxies has been loud, public and continuous, conducted in the open across hundreds of papers, which is precisely what a healthy unsolved problem looks like. The instinct that a shocking discovery must mean the experts were lying gets the truth exactly backwards. The shock is in the literature because the experts told you about it. Being unsettled in public is the most trustworthy thing science does. So the crack will not fully close, and we should not pretend it has. The black holes explain a great deal, the faster star formation explains more, and between them the worst of the impossibility has been absorbed. But the Hubble tension sits in the background, unresolved, an independent reminder that our timekeeping is a work in progress. We do not yet know, with certainty, whether the early universe merely worked faster than we imagined, or whether some more fundamental revision of our picture is waiting to be made. We are in the middle of the story, not the end of it. And that, far from being a reason for fear, turns out to be the most remarkable thing about the whole situation, once you see it clearly. To understand why, we have to return one last time to the phrase in the title, and ask what older than the universe has really meant, every single time we have ever said it. Part 12. What older than the universe really means. We have arrived, after a long night, at the phrase itself, and we can finally say plainly what it means. Older than the universe is one of the recurring sentences of astronomy. It has been spoken, in genuine seriousness, by careful people staring at careful measurements, more than once across the history of the science. And here is the thing that should change how it sits in your chest. It has never once turned out to mean what it literally says. Not a single time. There has never been an object truly older than the cosmos that contains it, because that is a logical impossibility, a child older than its parent. Every time the phrase has been spoken, it has meant something else, and the something else has always been the same. It has always meant that two of our measurements disagreed with each other. In the 1990s, it meant the measured ages of the oldest stars disagreed with the measured age of the universe, and the disagreement dissolved when better distances and the discovery of dark energy sharpened both numbers into agreement, teaching us about the accelerating expansion in the process. In the 2020s, it has meant that the apparent maturity of the earliest galaxies disagreed with our theory of how fast galaxies can be built, and the disagreement has been easing as we learn that black holes were inflating the masses and that the early universe built stars faster and brighter than we knew. The pattern is identical across the decades. A measurement collides with a model or with another measurement. The collision feels for a while like the universe breaking, and then the collision turns out to be a door, and on the other side of the door is something we did not previously understand. Let me return the other phrases we have carried through the night, because they deserve their endings too. When the universe breakers were announced, the honest reaction was that someone had discovered the impossible. And for a year or two, that is what it looked like. But the impossible turned out to be possible the moment we understood what the light was actually made of. The moment we realized that some of the glow we had credited to an impossible host of stars was really the light of black holes, and that the stars themselves had formed faster and burned brighter than our models allowed. The impossible became the not yet understood, and the not yet understood became, step by step, the understood. That is the journey nearly every great anomaly takes. It begins as impossible and ends as a new chapter in the textbook, and the word impossible, spoken honestly in the middle, was never a verdict. It was a confession that we had reached the edge of what we knew, which is the most exciting place a scientist can stand. And the clock and the story, the two things I asked you to hold against each other, we established the clock with real care, and we found it trustworthy. And then we found, in the Hubble tension, that even a trustworthy clock is still a measurement that can move. The lesson is not that the clock is unreliable. The lesson is humility about the difference between a measurement and a law. The age of the universe is a measurement, one of the finest we have ever made, and it is also not a commandment carved into reality. Whenever the clock and the story disagree, one of them is about to be corrected, and the correction is never a catastrophe. It is always a gift. It is the universe handing us a better version of itself than the one we had. So consider where that leaves the title we began with, the galaxies at the edge of the universe that terrify astronomers. The terror was real. The astronomers who first saw those impossible masses felt the floor tilt, and they were right to feel it, because the result genuinely threatened to break something they trusted. But terror is the first response, not the final one. The final response, once you understand the history and the physics and the recurring shape of these crises, is not terror at all. It is something closer to gratitude. We are alive in the precise decade when the most settled number in cosmology started asking questions again. We built a gold mirror, flew it out into the cold, cooled it to almost nothing, and pointed it at the dawn of everything, and the dawn refused to behave the way our model said it should. That refusal is not a horror. It is the universe doing the one thing that keeps science alive, which is to be stranger and more capable than we assumed, and to tell us so in light that has been travelling toward us for more than 13 billion years. There is a particular privilege in living through a moment like this, and I want to leave you holding it rather than holding the fear. Most of the time, the great questions feel closed. The textbooks are written, the numbers are fixed, the story is told, and it can feel as though all the genuine astonishment belongs to the past, to the people who first measured the expansion or first saw the ancient glow. But every so often, the universe cracks one of its settled facts back open, and for a little while we get to stand in the unknown again, looking at light from the beginning of time and arguing about what it means. We do not yet know, with certainty, whether the early universe merely worked faster than we imagined, or whether something more fundamental is waiting to be revised. We are in the middle of the story, and the middle of the story is not a frightening place to be. It is the most alive place there is, the only place where discovery actually happens. It is worth saying clearly, before we let the night close, what this whole episode reveals about the way knowledge actually grows, because it is the opposite of how we are often taught to imagine it. We tend to picture science as a smooth accumulation of certainties, each fact locked into place and never disturbed again, the textbook growing thicker and more settled with every passing year. But that is not how it really moves. It moves through exactly the kind of moment we have spent this night inside, a moment where a careful measurement collides with a trusted expectation and refuses to back down. The collision feels, at first, like a threat, like something precious is about to be lost, and then slowly it turns out to be the engine of the next understanding. The discomfort is not a sign that the method is failing. The discomfort is the method, working exactly as it should, refusing to let us rest in a picture that the evidence has outgrown. That is why the right feeling to carry out of all this is not fear, and it is not even relief, but a kind of quiet trust. Trust not in any particular answer, because the answers are still being worked out, but in the process that produced both the shock and the slow unravelling of it. The same field that announced these galaxies as impossible is the field that is patiently explaining them, and it is doing both in the open, in full view, arguing with itself in public, correcting itself in public, exactly as it should. There is no authority handing down certainties from above and hiding the cracks. There is only a community of careful people looking at the oldest light there is, and trying, honestly and imperfectly and together, to understand what it is telling them. When you see that clearly, the galaxies at the edge of time stop being a horror story and become something closer to a portrait of us at our best, reaching past the limit of what we know and being willing to be surprised by what we find. So tonight, as you let yourself drift, you can let the fear go with the day. You will sleep under a sky whose darkest, longest exposure images contain objects we cannot yet fully explain. Galaxies at the very edge of what can be seen that wear the appearance of more history than history could supply. That is not a thing to dread. It is the rarest gift a curious mind can be given, to be born into the exact decade when a long quiet number began to speak again, and to be here, watching, while the answer slowly takes shape. The galaxies at the edge of time do not truly threaten the universe, or the clock, or you. They only ask us to look more carefully, and to hold our certainties a little more gently, and to remember that older than the universe has never once meant a paradox. It has only ever meant that something wonderful was about to be understood, and that something is still out there, in the oldest light there is, waiting for the morning and for us.